we'll start recording. Okay, so we're recording now. So all I've done is I've just shown the last week of semester 1 schedule and given you time on the warm-up problem. We've talked about study strategies, and I've talked about the final, and they're in the slides. Okay, so here we go. What's next? I want to talk about my office hours for the rest of the semester. So because this week and next week are 4-day weeks, we don't have the normal Wednesday schedule with office hours. So I'm going to hold Zoom office hours this week on Friday. Okay, so Friday afternoon I'm available for an hour. Also want to let you know that next week I'll be available every afternoon, Monday to Thursday, 12:45 to 2 o'clock. Okay. I also want to make sure you know that if for some reason you can't make one of these office hours, or you just really, it would work better for you to have just kind of an individual one-on-one quick conversation with me about a problem or a question or a concept, I'm happy to do that. I've had students reach out to me and say, Mr. Bob, is there a time we can meet one-on-one? And I've set up that time with you, and I'm happy to set up that time with you. So just email me or send me a message and remind that we can set up a time that will work. Okay, so those are office hours. Okay. Also, forecasting for next year, I know is happening right now. And I know you are submitting your forecast sheets, those of you who are not seniors. So in case you missed my presentation about IB physics, understanding more about HL and the SL program, please feel free to reach out to me. I also have, recorded the session. All the sessions have been recorded, but I don't know how soon they're going to release them to you. So the video about IB physics, the link I'm about to put in the chat here, bit.ly/chsIB physics video. It's right there in case you want to watch that. And also, I just want to emphasize that, again, I'm happy to have conversations with you if you feel like you're trying to figure out what would be a best fit for you and if HL physics is a good fit or whatever, okay? And then Dwight from the office has a message for you. And who out there's an Office fan? Basically, the deadline to submit, if you have past work that you want to submit for semester 1, 4:00 p.m. next Thursday is the deadline. Okay. I do encourage you to look and submit previous assignments, right? Look for the ones where you have a 0 in the grade book. Those would be the ones that I would look at first. Okay, and especially in the higher point value ones, the more they're going to be affecting your grade. So think about that. I just want to emphasize again, I do not penalize for late work. So you can still submit assignments from weeks or months ago, and you still are eligible to get full credit, assuming you do a good enough job on it. So keep that in mind. Okay. I want to give you a second, pull out the focus notes you took related to Newton's second law from last class. We're going to revisit them. So let me give you about 30 seconds here to get set up there. Not going to be a lot of notes, but it's just a couple of important points I want to make. Points that were brought up by many of you when you did the match that free body diagram work last week. All right, so let's talk about the warm-up problem. I'm going to walk through solution to it. So in this warm-up problem, I presented a situation to you where a student is pushing a box on the floor to the right, and I take 2 snapshots in time of that box, and I ask you to draw a free body diagram of the box for each of those moments in time. And the first moment is this point where the student, the box is going from a stationary sort of state of motion or non-motion. It's speeding up, okay? So these are keywords you want to key in on whenever you read a problem statement and you're asked to draw a free body diagram. Okay, so in this case, again, I'm going to reduce the free body diagram like free body diagrams do, reduce the box to a point. And in the vertical direction, what do we have? We have gravity pulling down on the box, and because it's sitting on that flat surface, you can see there's a normal force that is pushing up from the floor onto the box. And we can denote that these are equal to each other because it doesn't say anything about the box moving in the vertical direction. So since it's to the right, I could have said horizontally just to make sure that's really clear, but I'm going to denote that these forces are equal to each other with a hash mark like that. Okay, now what's happening left and right? Well, we know that there's an applied force because the student is pushing on it, so I'm going to make that. And there's friction. And the question is, how do you know how big to make the friction? And the key here is the fact that this says that this box is speeding up. And that tells us that the box is accelerating to right. And if it's accelerating, notice, remember Newton's second law, net force equals mass times acceleration. If something's accelerating, there has to be a net force, which means the sum of all forces, I'm going to say this is in the x direction, the sum of all forces in the x direction cannot equal 0, right? Because if it did equal 0, there would be no acceleration. So that means that the friction force must be smaller than the applied force at this moment in time, moment 1. So your free body diagram should look something like this for moment 1, with the applied force significantly greater than the friction force. Okay, let's jump over to moment 2. Now here we read the box is already moving. The student continues to apply a force such that the box keeps moving at a constant speed as it slides across the floor. Okay, so in this scenario, there are a couple things that are the same, and vertically there's no difference, right? The box still isn't changing its motion in the vertical direction. So we still have a gravitational force and we still have a normal force that are acting vertically, but equal in size. Now, what's going on here on the horizontal direction? Well, let's think about this. If the acceleration is 0, and we know it's 0 because it says constant speed, it's not changing direction, then that means what? The net force in the x direction has to equal 0. And that means the sum of the forces in the x direction has to equal 0. Okay, so what that means is in this scenario, my applied force and my friction force now match each other. And I can show with the hash marks there that they match each other. And I so appreciate those of you who did the match the free body diagram problem and brought up for me kind of the point of confusion you were having, which, by the way, you're not alone. For centuries, people have had this point of confusion. It took scientists Galileo and Newton kind of reimagining the paradigm that we live in to help people to understand this idea that an object does not need a net force to keep it moving. A lot of you said, well, it should have an arrow to the right because it's moving to the right. And that's understandable, you would think that way, but the way you want to recast your mind or rethink these things is in the absence of a net force, objects will keep their current state of motion. So in other words, if you get a box moving or any object moving, all you need to do is just make sure the net force on it remains at 0 and it'll keep moving at that same speed in that same direction. Okay, that's a key shift, fundamental shift in understanding what's going on here. So, so I'm going to go to the next slide because this is one of, there's 2 misconceptions I want to lay out, and I kind of just talked about it, but I want to formalize a little bit. So misconception number 1 that many physics students and many people for millennia have had is that you need a net force for an object to be moving or stay moving. And that's just false. And I'm lining that out just to make sure you know that's false. Because the truth is you need a net force to change an object's motion, meaning either speeding it up, slowing it down, or changing its direction. And if we speed up, slow down, or change the direction of an object, we have a fancy word for that. We've been using it already this year, acceleration. Okay. So again, net forces are required to change an object's motion, not to keep objects moving. A prime example of this, just an FYI, is way back in the 70s, NASA launched this space probe called Voyager 2. And it was launched in the late 70s. And certainly when it was launched, to get it moving, they strapped it on top of a rocket, and that rocket was super powerful, and it got it up into, outside of Earth's gravitational pull and got it moving away from the Earth. But since then, for decades now, that space probe has been moving with no net force on it, okay? And it continues to move. And in fact, in 2018, NASA estimates that it actually left our solar system without any sort of motor or sort of engine on it to basically propel it through space. The only power source it has on it is just to run the transmitters that basically it uses to communicate back with us here on Earth. So this is a prime example of how objects, in the absence of friction, right, they'll just keep moving. Here on Earth, we're kind of saddled with friction and air drag and air resistance all around us, so it's hard for us to see it that way. The second misconception that I heard a lot of you say, and this is honestly happens every year, I'm so glad those of you who voiced it, is a lot of you said, if there's a velocity to the right, then there should be an arrow, some sort of net arrow to the right, or to the left, or angled up and to the right if a ball is moving up and to the right. And so this brings up another misconception about free body diagrams that I want to disabuse you of. Free body diagrams do not show anything about velocity vectors. They're not velocity vectors, okay? What free body diagrams are is they show force vectors. And remember, by Newton's second law, force vectors are related to acceleration, not to velocity. So when you look at a free body diagram, it really tells you nothing about the initial conditions, the initial motion of the object, just looking at the diagram itself. You actually have to read the problem statement to get a sense for what's going on, what the initial conditions are of the object's motion, okay? So in other words, this last sentence here kind of says that the free body diagrams tell you nothing about an object's initial velocity. You have to read a problem statement to learn about that. Okay, so these are two important ideas that I think you should add to your notes in some way or another in your own style, because they're things that are commonly misconstrued by students, and they're important to keep in mind going forward. Okay, so who's ready for a joke? Thank you, Hudson. I see Hudson's hand. What did the DJ say at the root vegetable dance party? Let us turn up some beats.
Ha 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 ha.
I have to give credit to another science teacher. Some of you may know Mr. Fuller. He is the one that shared that joke with me. So thank you, Palace. Appreciate the haha. And speaking of, let's go to the next slide. Let us apply what we just learned. Oh, another pun. Yes. Thank you, Daniel and Sal. So this is a problem that was in the match the free body diagram thing. So I'd like you to go ahead and read it, the problem statement there, and look at the two diagrams I've shown you and which free body diagram is correct, and explain it to yourself out loud in words. Take 20 seconds to pick which diagram is correct and why you think it's correct. Go. Okay, hopefully you talked about the fact that diagram 2 is correct. And because it's at a constant speed, the custodian is pushing the crate at a constant speed. That means the sum of forces in the horizontal direction have to be 0, no net force. Therefore, this is the diagram 2 drawn is the one that shows the two force vectors in the horizontal direction being equal to each other. Awesome. Okay. So here's what I want to do. I want to give you a 5-minute break. And in that break, I want you to take the first 90 seconds to watch this video. This video, I've noticed, and I've observed it enough that I'm worried that students might still be out there basically looking at their grades, but not looking at them correctly. I think the default viewing that Canvas puts you into is for quarter 2. Thank you, Sal. And I'm worried that some of you may be looking at quarter 2 grades for this class or another class, and you might be into you might have a shock next week, say, when you realize that's not been the case. So go ahead and watch this 90-second video, and then whatever time you have left, you can obviously go into Canvas and make sure you know how to do it correctly, or just take the rest of the time for a break. And we get back in 5 minutes. We're going to go into breakout rooms, and I'll tell you what we're going to do then. And I'm not going to play music during the break because you need to watch this video. Okay, so please be back in 5 minutes. All right, welcome back, everyone. Welcome back. So here's what's going to happen. I'd like you, all of you, to pull up on your own the the link there, this is 5th period, should be bit.ly FBD elevator 5. There it is, bit.ly FBD elevator 5. Also, for solution key, at least one of you in your group should bring this up. That would be bit.ly/solution FBD-elevator. Okay, so what you're going to be doing is there's a series of free body diagram scenarios that you're going to be drawing free body diagrams for them as a group. Find your group slides, obviously, as usual. And then there's an elevator problem. That's a third problem there that's going to walk you through multiple parts to it, okay? So, so what you want to do is, here's what I don't want to see happen. Sometimes students are like, oh, I'll do number 1, you do number 2, and you do number 3, and we'll get it done really quickly. No, the goal here is for you to have conversations with each other, right? To make sure everyone understands and agrees. And if there's confusion or if there's difference of opinion, great, talk them out and then seek help from either myself, Sal, consult the solution key as necessary to kind of figure it out, okay? So that's really important. That's what's most important. You have plenty of time here. It's 9:47 and this class doesn't end until 10:30. So you have a good 35 minutes. I'm going to put one more link into the chat because some of you may finish early. And if you do, let me put this link. Turd the target 2. Remember you were trying to protect the grass, the field from that birdie's poops. So Turd the Target 2 is the sequel, and it basically has a challenge of they are angled projectiles now. So if you finish all 3 pages of your slides, all 3 slides, finish all the work, check it, you all feel good about it, and you still have time left, then please turn your attention to Turd the Target 2. And there's the link for it. Or you can just type in Turd the Target 2 physics classroom in a Google browser, in any sort of Google search engine, it will come up, okay? All right, so, and as usual, Sal and I will visit. Mr. McClary is not here today, but he will be back soon. Okay, so I think we're all set. So let's do this and have some fun, learn some physics, and enjoy each other's company, okay?